to see whether accommodation will trigger an increase in corneal power. So one thing you can do is to measure the corneal power both before and after accommodation. And of course, they find that the corneal power remain more or less constant, okay, during accommodation. So that means the accommodation is not triggered by an increase in corneal power. The second possibility is that the power change could be due to a change in the axial length. Okay, so that would be another possibility. And again, in order to rule out this possibility, so one thing you can do is, of course, like the diagram shown here. So you can measure the axial length and also measure the position of different ocular component using A scan. So this is A scan. Okay, remember. So this is um, the A scan ultrasound. So this is the retina, and so this is the posterior lens. This is anterior lens surface, cornea, and the tears. Okay, so and experimentally, what you can do is to present objects at different distance and to check whether there's any change in the axial length. And of course, the people find that there's no change. There was no change in axial length after accommodation. The other possibility is due to a change in the position of the refractive component. In particular, I think the lens. I mean, because you don't see any change in the axial length, so presumably it should not affect the cornea. Okay, so even if it affects the position, it would affect the position of the ocular component that is inside the eyeball. So which is one of the possibility is the crystalline lens, and therefore assuming this A scan, so you can also look at, for example, like a position C and position D, and to see whether there's any change in terms of the lens thickness. I hope you still remember this. From B to C is the anterior chamber depth, from C to D is the lens thickness, and from D to the retina is the which is VCD, is which is chamber depth. Okay, so later on, people realize that when you accommodate, actually the change is primarily caused by the change in the shape of the lens. The lens become thicker when people accommodate, just like this diagram. So this is when you look at distant objects, the bottom panel, as you can see, as highlighted by the yellow line. So this is when you look at a distant object. Okay, so when you can see when you look at a distant objects, you will have a sharp image on the fundus, on the retina, and instead during this process, I mean, when you're looking at a distant objects, so the lens usually will have will adopt its thinnest position. So the lens is usually very thin and having a very small, relatively small total power. And at the same time, if you look at near objects, of course, these near objects will not form a sharp image on the retina. Instead, you will probably see a blur image on the retina because the image of this object, near objects, will be forming somewhere here. I mean, the image of these objects will be forming somewhere behind the retina, and that's why you only see a blur image on the retina. When you accommodate, meaning that you will try to shift from this position and to another position. Here you can see the lens will become rounder, okay, more spherical, and the total power of the eye will also be increased, such that these objects will now be able to form a sharp image on the retina, okay, by increasing the total power. But when you do this, you would expect the object, which was originally at distance, will now, because of the increase in power, now will be forming an image or in front of the retina. So on retina, so you will have a blur image for the distant objects. Okay, and this is how the accommodation work. In fish, as you know, in human, the accommodation is achieved by having like a more spherical lens, so the lens thickness increase, and therefore to increase the total power. But in the fish, the accommodation is usually achieved by having uh, uh, the which is very hard. I mean, it is a hard spherical lens. So when it is hard, that means the shape cannot be changed quite easily. So instead of changing the lens thickness, what they can do is to move, I mean, to change the position of the lens. But it could be nearer to or further from the retina, and that would change the power of the, I mean, change the power of the crystalline lens as well by changing the position. Okay. Not only in fish, actually in rodent, for example, like mouse or rat. So the size of the lens is even bigger as compared to the size of the eye. So in the mouse or in the rat, the lens will take up primarily most of the space um, of the eyeball, so leaving very small amounts of the, for example, like a witches behind the lens and a very tiny space for the anterior chamber, okay, in the mouse. So as I just mentioned, so A-scan ultrasound is one of the techniques that we can use to check if the lens change in thickness during accommodation. The other experiments that the researcher did is to look at the change of the lens shape during accommodation, particularly in human. So one thing they can do is to use the Purkinje image. I think we have also discussed this in the previous lecture. Okay, and when the patient accommodate, I mean, if you still remember, here are the three major Purkinje image. Image number 1, okay, which usually is the brightest one. Okay, image number 3. So 3 is from the anterior surface of the crystalline lens. 4 is from the posterior lens surface reflection. Okay, so by looking at the position and also the size of the Purkinje image before and after accommodation, then you will have some idea about whether there is any change in the posterior or anterior surface of the lens during accommodation. Okay? And this was supported by the aphakic patient. Aphakic, that means the patient doesn't have a crystalline lens. So for those who do not have a crystalline lens, of course, you might not be able to see the Purkinje image 3 and 4. So suggesting that for this patient, if they don't have the crystalline lens, they can accommodate. So this is another evidence to suggest that the lens is the major component responsible for accommodation. And of course, the change in the shape and also the size of these two images, 3 and 4. Of course, you can also look at the image number 1 as well. But as you can see here, so image number 1 will not change in size and shape when you accommodate. So further suggests that the accommodation is not mediated by any change in the cornea. So the change in the shape and also the size is due to the change of the lens curvature. I think this slide just shows you the anatomy of accommodation before, this is a distance, and after accommodation. I think you should be very familiar with this. So I don't want to spend much time on it, but just want to show you the key things. Okay, so for a distant vision, when we don't have accommodation, so it's accommodated. So usually the ciliary body or the ciliary muscle should be in a relaxed position. So that's why the fibers will be in tension. Okay, and therefore, so you can actually have a so as you can see, this ligament in direct contact with is firmly attached to the lens, particularly at the equator, and therefore the lens will adopt this position, this kind of shape. So it will achieve its thinnest position, having the smallest dioptric power. So that's why you can look at the object at distance. Okay, but for when you accommodate, so the ciliary body or ciliary muscle will contract and remove this tension, and so the lens will adopt is like a more natural or relaxed position. So you can see that it become more rounded and having an increase in the ocular dioptric power. Okay, and that's why you can look at the object at near and be able to form a sharp image on the retina. So these are the major steps involved in accommodation, and I'm sure you have done all these in your anatomy as well. So I think the key thing is that the accommodation is innervated by the C3, okay, C3, causing the muscle, the ciliary muscle to contract, okay. So when you contract, then you can accommodate, and when you contract the suspensory ligament, so the tension will be removed, okay, and then so it will remove the tension on the lens capsule as well. Therefore, the lens will become thickened, and causing, in this case, will be causing a decrease in the anterior chamber depth because of the increase in the thickness. Because the eyeball size usually remain constant. So when the lens thickness increase, because in the posterior chamber we have the gel, and the gel is like jelly jelly, it can be compressed. Okay, it's non-compressible, and that's why whenever the lens become thicker, then there will be a corresponding reduce in the anterior chamber depth. And we can see that the major change happened in the anterior surface, okay, rather than the posterior surface. For example, according to some studies, okay, if you present a stimulus, 8 diopter of stimulus, okay, that means the objects will be located at about 12.5 centimeter in front of the patient, and so that you can see that at the anterior lens surface, so the rate of curvature will change by almost like a